My name is Martin Hadley. I'm technical presenter with Wolfram. So I'm not a computer-based math person. I'm a Wolfram research person. That's not to say that I don't see the usefulness of computer-based maths. I know for a fact I'd be better at my job if I was taught computer-based maths as opposed to the math I was taught, seeing as all I do all day is program. But I do know Wolfram technologies. I know what Wolfram technologies are used for at the cutting edge of research and also at the cutting edge of consumer devices and consumer interaction with technology as well. So, as part of this presentation, I'd like to consider two questions, really. The first is, where can computation get us? I'll start by looking at solving math problems, the kind of problems that you encounter in your education at the moment, polynomials, differential equations, linear algebra, and then I'll look at how these appear in exams. I'll then look at mathematics beyond the classroom, so what you can do with mathematics when you really put your mind to it. And then we'll quickly look at data and statistics and how you need computing, or you need a computable platform in order to do big data analysis. You just can't do it by hand, and that's where you need to learn computer-based methods from a very early age. And then I'm going to talk about why we're talking about CBM now. What's changed in the platform and what's changed in the way we interact with technology that we can actually talk about having a computer-based maths syllabus rather than the current syllabus that we have. So if I start by looking at solving math problems, most people think that math is solving equations. And that's ultimately a problem with our education system. It's much more than that. But let's take a moment to look at how we solve expressions in education at the moment. So when we're first given a polynomial expression in school, we're giving a quadratic equation that can be factorized. So it's very easy to solve, and we're also given a quadratic equation so we can extract real roots from the function. And students think that polynomials are very easy. But once they start exploring just quadratic equations, they see that they're actually very complicated outputs. So as we start to play with the coefficients of the quadratic equation, we see that we have imaginary numbers as part of our roots, and those are difficult concepts to understand. And as we move to high-order polynomials, the roots become more and more complex. And when we introduce quartic equations, the roots become very complex. And while there are hand-cranking methods to solve quartic equations, so you can solve a quartic equation by hand, it takes a lot of time. And also it also introduces a lot of potential error into your computation. So these are considered to be easy polynomial expressions, but actually what we're doing is we're giving a very small subset of the possible polynomial expressions to students to solve. And these are just the easy polynomial expressions. Once we move to more complicated things, we see that the actual results are virtually unfathomable by hand methods alone. You need a computable platform to do it. One other thing in polynomial expressions is that we're given very few tools to solve trigonometric expressions. We're given a few identities that allow us to solve very, very simple expressions, and there are a very small subset of those. But when you move to expressions like this, we have no way of solving those given to us in schools. We need a computable platform to actually interact with these problems and to understand them. And when we move to more difficult polynomial expressions, like quintic expressions and above, there are no general solutions for these. These are not problems that you can solve by hand. And so we have to question, to an extent, what the point is in giving methods to solve a small subset of quadratic equations and then a general method to solve quartic equations, which you never really use because it takes too long and you make too many errors. We give these tools, but then these tools can't be applied to larger, more difficult problems that you'd actually experience in the real world. So if we move on from polynomial expressions to differential equations. General calculus is, so differentiation relies on the range of tools that you taught in school, and you can perform those relatively easy, but as expressions become more and more complex, it's more and more stages by hand to get the solution out, and you introduce error into your computation. Integration is a more dangerous beast. Integration is more complicated. For very simple expressions, it's essentially the opposite of differentiation. But once you have an integrand like this, you end up with a solution which doesn't make much sense without a computable platform to explore what that equation actually means. And that's also not an integration that you would ever try and solve by hand. So that's general calculus. So differential equations are descriptions of systems that change. And these differential equations provide access to the underlying behavior of a system. And so we can do these in computable platforms very easily, whereas by hand, we're given very special cases of differential equations that can be solved. Okay. So with differential equations, we can go away and do interesting things, like we can simulate a bouncing ball with a specified coefficient of restitution. Here we've got quite a high coefficient of restitution of 95. And we can simulate a ball bouncing along, and we see that the maximum height is decreasing because energy is being lost to the surface it's bouncing on. And with a computable platform, we can actually extend this to generate an interactive interface. So now we're changing the coefficient of restitution, which is given a variable c, and we're seeing the bounces are further and further. And we can also change the size of the steps. And so that's something that we can do in a computable platform that we can't do by hand. And that's because we don't even have the tools to solve differential equations like this by hand. So it's a problem with a method, not just a platform. So linear algebra is a problem that's very well suited to computers because it's just performing the same operation again and again and again. So I'll just show you. So matrices are very useful are very useful constructs for solving systems of equations. You provide your coefficients as one matrix and your variables as another matrix, and then your solutions as another matrix, and you solve this expression using linear solve. And for a small matrix such as this, my variables may have had assignments to them in there. So for very small systems like this, we can do this problem by hand. What we can't do is we can't solve a matrix of equations which contains 100,000 elements. I can create in a computable platform a matrix containing 100,000 elements. And I can ask for a matrix plot of that, and we can see that I've got a matrix which is essentially empty. This is why we're using sparse array, because it's more computationally efficient to hold the data in sparse array than a matrix. And we see the matrix only has values along the diagonal. But what we can do is we can solve this system of equations in a realistic amount of time. In fact, here we can see it's taken milliseconds to solve 100,000 equations that you would just never attempt to solve by hand. Okay. So having seen that I can solve these problems using Mathematica, which, by the way, is the technology I'm using here, I thought that it would be quite interesting to go away and try an exam paper. So the first question in the exam paper is to express this in the form of a plus b, so just surge really, and it just takes one line in a computation platform to perform that. So that's a very simple problem that we can solve, and it doesn't really give us any information about a problem that we can do it like this. And seeing as this is the platform that people use to solve real-world problems, what's the point in giving this kind of problem to a student to solve by pen and paper when in the real world they're going to solve it in a computer and it's not a problem that requires any understanding? So let's go on to a more complicated problem. So these are very simple problems to solve on a computer, obviously. There's some more interesting questions down here. So this is quite an interesting question in the exam paper. So we're given the equation for a curve, and we're asked to find the minimum coordinates, the coordinates at the minimum point. And so in Mathematica, all I need to do is define a function, and I've put a plot in here just so I'm visualizing it, so I get an extra mark in the exam paper. And I can just apply the function find minimum to find minimum, and that's all I'm doing. So I'm not really exploring the problem at all, and this question isn't really challenging in any sort of way, because it's not asking you to understand the expression or understand the principles behind the maths that you're performing. So the most complicated question on a paper is always the last one. So the most complicated question is, a circle has center -2, 4. And so I've happened to remember from my school days the equation for a circle, which is that, nice identity that. And I've got a contour plot of that, so I've visualized my expression. And it wants me to find the equation of the circle giving my answer in this form. So I get my expression as the equation of a circle, and then I apply the function expand all to that. Now, I know that I need to range it equal to 0 because I won't get my final mark in the exam. So what I need to do is I need to subtract that expression to equals, and that rearranges my expression set to equal to 0. And I've got 4 points on that question. And this question just goes on and really doesn't develop my understanding of the equation of a circle or this problem at all. And also, I'll go back to this problem when I'm talking about interfaces in the next section. So having shown I can do an exam paper with Mathematica, I'll show mathematics beyond the curriculum. So control systems are a series of differential equations that are designed to return systems that are in an unstable equilibrium back to their equilibrium using a control force. So the only example that you'd get in education at the moment is a pendulum which you applied a small angle approximation to, and you get a very simplistic model of the pendulum which is completely false, as we know from experience, because this isn't a stiff rod, and there are other problems as well with the model. So we can go away, we can simulate a more complicated thing. So a Segway, I don't know if you've seen, but it's essentially an upside-down pendulum which needs to be constantly equilibrated. And it turns out that you can equilibrate that system using a differential equation of this form. So whether you perturbate your system, either by shoving it along or giving it or changing the angle of it, you can apply a controlling force to return it back to the origin and also make it straight forwards. So if we apply a very noisy signal to our upside-down pendulum, we can simulate what our pendulum does using this control force, and we can see as the bumps go higher, it gets further and further out, but the controlling force is bringing us back. So that's an example of control systems that you can build in computable platforms and Mathematica as well. So image processing is quite fun. So biomedical researchers need to count cells because they do things with cells, and they need a lot of cells in order to do those things. But they can't count them all by hand because it's impractical. Actually, I worked with people for a while who did do it by hand, and they were very upset about it. So it's something you can do with image processing very easily. So here's a microscopy image of a small number of cells, which we can give to Mathematica. And we can do some small image processing on it to make it a simpler problem. And then we can perform some image analysis on this to identify individual cells in this using a max detect function. And then we can also perform some Mathematica magic, which I happen to know how to do, to get out this, which is our original microscopy image with each of the detected cells overlaid on top with a nice disk. So that's something that real people do with image processing. Another thing people do is in medical imaging. So medical imaging, for quite some time now, people have been interacting with three-dimensional images, and it gives a lot of data about the outside of a system, but doesn't give any information about the inside of a system, the interior. For that, you need to take three-dimensional slices of that system. So here we have that 3D model that we're sending through a 3D slicer, and we're seeing it, we're moving through that 3D image, and if there is an object of curiosity, then we would be able to show that. Okay. So signal processing is operating with noisy functions.
You will return safely to Earth.
So this is a very noisy recording which I'm applying some simple equalizer function to make it sound slightly nicer.
You will return safely to Earth. You will return safely to Earth.
And because I'm not a sound engineer, I can't get it to sound any better than that. So data and statistics. So by hand, you can handle a very small data set like this. So this is a data set where we randomly generate a series of boys and girls whose parents have a particular income and they have a particular height. We're actually creating this data ourselves, and we're explicitly saying that if you have a higher parental income, you're going to be taller. So let's go and analyze that using hand methods. We could analyze that using hand methods and build a histogram of that data. And we can perform analysis on that. So here we're trying to see whether there is a difference in height according to parental income, and we can see that we have extremely small confidence that there is any change, and we also have an English output of this test, which is saying that the test is failing to perform, despite the fact that we've generated this data and we know this data is biased, so we should be able to do that. And it turns out that you can't do that because it's too small a data sample. You need a big data sample. So we've performed a big data sample. We've generated a big data sample with 10,000 members in it. And this is the histogram. And this is not a problem that you'd be able to solve by hand. You wouldn't bin this data by hand, and you also wouldn't plot the histogram. And with a computable platform, we can do more interesting things, like we can look at a three-dimensional histogram to try and see underlying trends. And there's not very many because we didn't choose the distribution correctly. And we can also interrogate the data in different ways. So we can look at the distribution of boys compared to girls. And when we perform our statistical analyses on this data, because we have enough data, we can actually see the underlying bias, and we have very high certainty that there is a difference between the mean height and the parental income, between height and parental income. Okay. Right. So this is the second part of my talk. Why are we talking about this now? So Conrad in his TED talk spoke about how we need to prepare people in school for real-world math. But this is a problem that we've been talking about for quite a while now. So why are we able to talk about this problem now when we haven't been able to talk about it before? And why are people so excited about being able to solve this problem now? One of the features is that programming languages are evolving. So the way that we perform computation using programming is evolving. So before, where we had, if we wanted to perform any type of computation at all, we would have to perform a relatively complicated loop function, where we go through a matrix and we add each row to create. So I've got a two-column matrix and I want to turn it into a one-column matrix by summing each of the rows. Older style programming languages require you to perform a do loop. Modern programming languages have built-in functions. So these are Mathematica functions, total transpose on that matrix, and you get your output here. And you can do more advanced things like looking for underlying patterns in your data and applying a rule onto those patterns. But a more interesting thing that's happening on top of the evolving programming languages is changes in interfaces. So I want to quickly look through the changing interfaces and look at the various quadrants in this matrix between open and closed platforms and precise and ambiguous input. So controlled experiences are probably the most ubiquitous new interface that we have available to us, because everyone has a smartphone and most people have a tablet as well. So app stores provide very controlled experiences. They provide pre-generated interactive and computable content. What that does is it provides a highly stable platform for computation. You're able to control the expectation and the interaction of your users with your data, and so you can ensure that they get very specific understanding from your app that you build. So interactive documents, one of the technologies that Wolfram Research has put out is the computable document format, which allows you to share fully computable document with anyone, and they can interact with that. One of the most useful features of the CDF is that you can build manipulates. So here I've got a little interactive toy where I'm interacting with a damped oscillatory function. And I'll just show you how easy it is to build a little toy like this. So I've just very quickly created a little interactive toy that allows me to play with beat frequencies. So I've got two sinusoidal functions which are being added together, and I can see what happens as I change the frequency of those. So I can introduce beats, and I can also change the frequency of those beats. And that's something that you can do because of evolving programming languages in very little coding. And this little interactive toy that I've made, I can then deploy to anyone I want using the CDF document standard. If you're interested in what you can do with CDFs and the manipulate environment in general, then I couldn't recommend more going to the demonstrations.wolfram.com website. You can go and you can interact with any of these examples completely for free by downloading a free CDF player, and you can see what you can do using a controlled environment to impart understanding of a system. And also, if you happen to have Mathematica, you can actually download the source code and steal these examples, and that's completely fine. So on top of interactive documents, it's very important to be able to interact with geometries. So I've just got an example here which helps us explore Sokotoa, and this is something that you would require a lot of work to understand by hand, whereas using a computable platform, you can actually understand Sokotoa a lot better by playing around with your variables rather than having to redraw your triangles every time. So I'd just like to apply this very quickly to the exam paper question. In question 7, I was told a curve had an equation, and I was told to find the coordinates and minimum point, justifying its minimum. And I just applied a find minimum function, but I could actually change it instead to a plot. And then I can wrap a manipulate function around that, and I can So using a manipulate, I can actually explore that expression much more than I would be able to do in the maths problem that I was set before. So if I move on from controlled experiences into accessible programming, so visual programming is something which is evolving in simulation environments a lot. So it's becoming possible now to create drag and drop models of very complex systems. So here in Wolfram System Modeler, we've modeled a satellite orbiting the Earth, and we can then interact with this simulation. So I've run this simulation using a drag and drop model, and then I can visualize where the satellite is at a specific time through the simulation. It will run. It will tell me where it is, and it will also compute for me the closest cities. And so this is something that you can do with visual simulation software that you wouldn't be able to do using other interfaces. So more powerfully in accessible programming, predictive interfaces are being introduced. If I provide a list, then Mathematica will suggest a bunch of things that you can do to that data. And if I provide it with a slightly more realistic data set, then I have the option of generating an interpolation function, and an interpolation function is a function that's explicitly defined as passing through each of these points, and then I can apply various things onto that, and that's something very powerful that you can do with predictive interfaces, that it lowers the barriers to new functionality and also new things that you can do with your problems. Okay, so free-form English input is one of the most interesting things you can do. So math problems. So with Wolfram Alpha inside of Mathematica, you can provide a free-form English input math problem, and you will get the code that you would have to write otherwise to compute this problem, and also the solution out. And you can do it for more complicated things as well. So we're not coding here at all, we're just providing free-form English input, and Wolfram Alpha is doing the magic for us. Wolfram Alpha also knows a lot of stuff. So you can ask Wolfram Alpha about a person, and you will get computable information on that. So one of the things we like to say is weather in Spain when David Cameron was 2 years old. So this is a math problem and a knowledge problem, and this is something that you can do in Wolfram Alpha if you go to wolframalpha.com, or if you have Mathematica, you can do within a Mathematica notebook. And here's a free-form English input correctly understood and computable data put out. You can also do much more interesting things, like if John has 5 apples and I give him 2 apples, how many apples does John have? So that's so natural language programming is evolving very, very quickly and is providing you with access to computing power which you wouldn't have without this interface. On top of free-form English input, you have computing personal assistants, who millions and millions of people have been using this natural language computation without realizing it. So let's see. Who is David Cameron? Let me think. Oh, you don't like that one, do you?
Okay, Martin, here you go.
Okay, and so because the webcam isn't working, you're going to have to look at my tiny screen. But I've gone away and asked Siri who David Cameron is, and it's gone and sent that input to Wolfram Alpha and given me the same feedback that I would have got if I searched in Mathematica or from the Wolfram Alpha website. And you can also ask them more complicated questions, which I asked Wolfram Alpha directly. And as these assistants are used more frequently, their knowledge of both the world and natural language improves, and they only get better. So a more universal form of natural input, actually, is handwriting recognition. Handwriting recognition has fewer language barriers to free-form English input because English input is English, whereas most people will write cos x, and it will look the same whoever's writing it. Well, it will compute the same whoever's writing it. And so this natural input can be converted into programmatic input and can be computed with using Wolfram Alpha. Okay. So the ubiquity of computing machines is also changing is also going to change computer-based maths, because we're bringing math into the physical world. So with tablets, you're able to interact with Wolfram Alpha in the same way that you can interact with it on a computer using free-form English input. You also have access to Wolfram apps, which provide you controlled environments. So the closing statements are that computing power, ubiquity, price, interfaces, and form factor are evolving radically. Computation and interfaces are changing, and we've not really seen anything yet. Thank you very much for listening.